some point I went to like, all the year and sometimes it was like,
I don't know if I'm going to keep taping because the quality is not all that exciting. And it looks like people are able to come to class in person. So I'll try it another day and see what happens.
it'd be great review material.
Yeah.
So we should all, like, half of us not show up for the next class.
Half of you not show up, and then I'll either keep recording or I'll give a pop quiz. All right. So, that's interesting. There we go. All right, so let me talk a little about lab write-ups, because there's a few people here who weren't in 250 with me. And in general, I just want to make sure everybody's on the same page as far as expectations for lab reports. So what I don't care about is what font you use, what you call your different sections, how you organize your title page, things like that. I'm not worried about, okay? The most important thing I'm worried about in a lab report is it needs to be a document that stands by itself. I don't want to have to look at the original lab assignment in order to understand the lab report, okay? So when you do homework, you read the question, calculate this, and you write the answer down on your homework sheet, right? That's not what you want to do for a lab report. If you were doing the same thing in a lab report, you should say, experiment 1, we're asked to calculate this value based on this equation, here's the calculations, here's the answer. And now somebody reading your lab report knows what this number is that you wrote down for the answer. So that's what you should be thinking of as you're writing your report. Experiment 1, we took some code and we put it into MPLAB-X, and we set a breakpoint, and we set these watch points, and this is what we did, and the machine crashed, so we rebooted it and started again, etc., etc. So you want to make sure that it explains exactly what you did. The goal of the lab report is somebody else should be able to read your report and reproduce your work. Okay, so this is the scientific method. You do an experiment, you get some results, you draw some conclusions, and then you publish your results. And other people read that and they reproduce what you did. So you want enough information in your lab reports that somebody else can do what you've done and confirm your results. Now it's a little different in 270, we're not quite doing like a chemistry lab, right, or a biology lab. The term experiment might not feel exactly the same, but it's the same principle, okay? So in experiment 2, you built this circuit, you put this code into your system, you ran it, and what happened? These LEDs blinked, and they blinked in a way that if you look at it as a binary number, it counts from 0 to 15, right? So that's what you want to say in your lab report. And you want the circuit diagram, and you want the code, and you want all of that in there, and then somebody else can take that and try to do the same thing. All right. Additionally, well, let's just pull up the lab. So you've got your experiments, you've got your descriptions, all of that sort of stuff. So report requirements, so they need to be computer printed. Okay, the exception is circuit diagrams. You can draw those by hand. Try to do it neatly. Okay, if you draw it on paper and you put it into your lab report, which is an electronic document, try to get a clean copy of it. Okay, if you use a bright light, you can do it with a camera phone. If you have a scanner, that works well. But whatever you put in your lab report, look at it with new eyes and say, can I actually tell what this says? Okay, is there enough detail here so you could actually rebuild that circuit? So for each experiment, clear statement of the problem, anything that it asks for specifically in the report, make sure that you address that. Okay, 'cause some of these experiments say, calculate this, or, describe that, and so on and so forth. Documentation of high-level design. So what do you want in here? Put in flowcharts or pseudocode, okay? Experiment, or lab one, don't worry about it, you didn't write the code, so I'm not gonna ask you to produce a flowchart for it, but for the other labs, you're gonna come up with code, put in some pseudocode, okay, or a flowchart, something that describes at a high level what your algorithm is. Because you don't want somebody to have to try to reverse engineer your assembly code. So, and writing this high level pseudocode helps you write the assembly language. And then disassembled code. So when you're in MPLab, if you go to window debugging output disassembly listing file, it will give you a nice copy of your source code, but it will also include the machine code version on the side. Okay, that's what I want you to include. And the first time you try to do it, it complains about something, and just follow the instructions, or ask me in lab, and we'll get you through it. So that's for each experiment. For the whole report, you want a cover page, okay, with your name, full name, the name of the person that you're working with in your lab group, and then the basic stuff, date, the course number, the lab number, and so on. At the end of your report, I want 2 additional sections. One talks about lessons learned. So think about, why did we have you do this lab, right? What were we hoping that you were going to gain from this, and what did you gain from it? Okay, if you've been doing programming in MPLab for 10 years, you probably didn't learn anything. But if you haven't done this before, what are some of the things that you learned? And give this some thought. Don't just say, I learned how to use MPLab X. Well, yeah, okay, that's true, but be a little more specific. Okay, what are the real take-homes from this? And it's likely to be different for each person. And then we want a new experiment. And this part frustrates students usually. And this can take you, 30, 45 minutes, an hour to come up with sometimes. Think about what you did in this lab. Think about the things that you were asked to do, the different steps, and how could you have taken some of these further, right, to come up with a new experiment. Try not to just take one of the experiments that we did and modify it. Let's build a circuit and write some code so that every time the input changes, it counts down instead of counting up. Technically, that's a new experiment, but try to be more creative, right? Think about, this is what I knew before the lab, and while I did the lab, I learned this, and that let me do this, and then let me do this. What if you wanted to go a little further? What if you wanted to extend your understanding into something a little deeper? What might you do as an experiment 3 in this case? So play around with that and write up a new experiment, and make sure the experiment you write up looks like an experiment. It tells the person what to do. If they need to build a circuit, what's the circuit they should build? If they need to write code, what should the code do, right? It's got to be detailed enough so that if you handed this to somebody else in class, they could do the experiment you described. So you can't just say, make a different program and connect it to some lights, right? If I told you that's the experiment you need to do today, what's the first thing you'd say? Give me more information, right? So put in enough information so somebody can actually do that experiment. I love this mouse, but every now and then it just dies. And there's no fixed procedure for bringing it back to life. There's steps we can take. That wasn't them. All right, so questions on lab write-up. So the labs get turned in electronically as a PDF. So if you're working in Word or OpenOffice, there's an export as PDF option, and that'll give you a PDF file you can upload to Canvas. If you're working in some other system, you may have to be more creative. Hey, I got my mouse back. All right, a couple of things that came up while people were doing labs on Tuesday. The first thing is sometimes you get everything wired up and you go through the software and you try to program your device and it complains about PIC-Kit2 not found or unexpected device error or something like that. In some cases those errors can be ignored. The ones about PIC-Kit2 not found seem to be ignorable as long as you can do the following steps. If it says unknown device or expecting 7E and got 00, or those kinds of errors, it usually means something's wired incorrectly. Something between the PIC-Kit2 and the chip. So this wiring down here. And more often than not, these two wires have been switched. But it could be the ground and power have been switched or something else. So double check that. All right, now in some cases, after you program the chip, it started working right away. And that's what's supposed to happen. You can actually drive this with the power and ground coming out of the PIC-Kit2. And if that works, it's really convenient because you've got this hooked up to, you know, your LEDs, and you've got your 555 coming in here on pin 1 and so on, and you program it and your LEDs just start blinking, and it's great. But in some cases that wasn't working. If it's not working, there's two possibilities. One, disconnect this wire and go ahead and pull this to 5 volts through a 1K ohm resistor, like it shows in the schematic down here. They show it with a switch, but the goal is really just to connect pin 4 to 5 volts. So that's one possibility. The other possibility that avoids all of this complication is do the following. On your proto board, put your PIC chip in here. Here's your PIC-Kit2. Right, and wire it up in the usual way. Program your chip, and then when you're done, pull your chip out, put it in over here, and have this be the actual circuit that you want to develop, right, with your 555 and your LEDs and so on. But physically remove this chip from the programmer, pop it in over here. Okay, that's the cleanest way to do this. You gotta be a little careful when you pull this out, because if you pull it awkwardly too many times, the legs break off. But if you just throw like a tip of a mechanical pencil under there and pry it up gently, it comes out pretty easily. So one of those options should work for you. The other possibility, and your results may vary, but in your kit you should have one of these little 6-pin angle connectors. I know it's impossible to see like that, but it's basically 6 little wires going down and they come out at right angles. And we put these in the kit for the following reason. What you can do is take this connector and pop it into your proto board somewhere and run wires from here to this as if you were going to program it with a PIC kit. And when you want to program it, take the PIC kit and just slide it onto these 6 connection points. And that electrically connects this to your PIC chip. Download your program. When it's done, just disconnect it. Now you don't have to change any wires, because the wires you have going from here to here don't do anything. Right? They're just open connections. So you don't have to move the chip then. You can go ahead and build your circuit around this. When you want to program it, pop this in. When you're done, take it out. That may be more trouble than it's worth, but it's a third option. Cleanest way, if you're having any trouble, program it over here, take the chip out, put it in here, use it like that. All right, questions on that? Let me take 5 or 6 minutes talk about breadboarding. Because this is the other thing that causes issues sometimes, is connecting a circuit on a protoboard. And let me pick on this 555 circuit for now. And we won't worry about the PIC chip connection, but let's just look at this 555 chip, because this is usually the ugliest chip to try to wire, because there's wires going all over the place, right? And if you get one wire wrong, it's not going to work. And figuring out which wire is wrong can take some effort. So let me suggest a way that I would wire this on a proto board. And this is not the way you have to do it, okay? But it's a way to sort of try to keep things as simple as possible and keep it relatively easy to debug. So let's imagine we have a proto board. I think they're going to have a band down there later. Let's make it noisy. So your proto board usually has two lines on the top and two lines on the bottom, and typically they're red and blue. And they may even be labeled positive and negative, but it doesn't really matter. And then you've got all these rows of holes running vertically all the way across. All right, so how could we wire up this chip? We always want our integrated circuits to straddle that middle region. So I'm just going to drop it down somewhere like this. And it's got 8 legs. All right, first thing I'm going to do is take my power supply and power supplies have 3 things on the bottom: negative, ground, and plus. We want to ignore ground, even though we always use the word ground. That's not what this is. Okay? This is actually called case ground. It's electrically connected to the outside of the power supply. What we really want is the negative output and the positive output. All right, so put an alligator clip in here, run it over to a jumper, connect that to the red line. Red is traditionally used for power, and blue or black is traditionally used for ground or negative. So plug that into the red line up there, and take the negative and plug that into the negative line. And I put them on opposite ends of the boards just to minimize the chance of them shorting. Right? Otherwise, if I put it up here, they're kind of close to each other and so on. And then over here, run a pair of jumpers. Connect your blue lines together, connect your red lines together. And I do that regardless what it is I'm about to wire. Why? Because now I've got 5 volts and ground on both sides of my board. And anytime I want to connect to VCC or ground, I can just run a little wire to one of those rails. And I don't have to cut across the board. I don't need long wires and so on. All right, so how do we wire this? Well, pin 1, it's off the screen, but pin 1 has to go to ground. So take this and just run a jumper to your ground line. Pin 1 is done. Pin 2 needs to connect to pin 6. All right, so we need this to connect to pin 6. So go into this line of holes and just run a wire over to pin 6. Pop it across the top of the chip. That takes care of this. Pin 2 needs to go through your capacitor to ground. So this is the big orange-yellow capacitor. Pin 2 goes to ground through a capacitor. Well, pop into a hole here, go into that capacitor, and plug the other end into ground. And you can do that without any wires. right? There's two big long leads on that capacitor. So just take one of them, pop it in the same row as pin 2, pop the other one into that blue rail. Now you've got this connection. Pin 2 and pin 7 get connected through a 1 meg. So take a 1 meg resistor, pop one lead in here. There's your 1 meg, pop the other lead on pin 7. So far I've only used one wire to actually connect this thing up. That was going from 2 to 6. And now I've got this in place. Pin 7 goes through a 1 mega ohm resistor to what? VCC. It also goes to pin 4, it also goes to pin 8, but VCC and ground are the easiest things to connect because we've got those power rails. So take your other 1 mega ohm resistor, plug one end into pin 7, and hook the other end up to VCC. All right, this capacitor is different. This is called a deflating capacitor. It's meant to smooth out power line fluctuations. It doesn't electrically connect VCC and ground, but if VCC starts to vary, it will smooth out those fluctuations. And for this lab, you can really just take your little 1 microfarad, plug one end into ground, one end into power, but do it physically close to the chip. The closer it is to the chip, the better it will work. And we'll come back and talk about this in a lot more detail when we start working with motors. But for now, just throw it in somewhere between power and ground. That takes care of this. Pin 8 should go to 5 volts. Well, here's pin 8. Take a wire, run it to your VCC line. And then pin 8 and pin 3 get connected through a 1K. So take this, go into your 1K, take the other lead, pop it next to pin 3. That takes care of this. And then pin 3 is also our output, so take a wire here, and that's going to go into pin 1 on our PIC chip. And you've got your whole 555 wired. And there's not a whole lot of wires. Did I miss one? I missed pin 4. 4 gets tied to VCC. Okay, so jumper from there, come down to VCC. Thank you. That's a 45-minute exercise in frustration if you don't do that. All right, does that make sense? So I'm laying it out kind of the way the picture is laid out, but I'm keeping my wires as minimal as possible. There's a lot of other ways you can do this, but if you take a wire from pin 2 and bring it over here, and take a wire from pin 7 and bring it over here, and then run a pair of wires from there up to here and put a resistor up here, it's just more wires to get in the way, more things that can get pulled out. And if you start trying to get fancy and say, well, this is actually going to connect to pin 8, and so you just put a resistor between here and pin 8, when you're trying to debug, that's not really what this circuit is saying. The first thing it's saying is that pin 7, 1 mega ohm resistor, 5 volts, right? So that's just a suggestion. But a big thing is putting these power rails on top and bottom, and then just connecting directly to those. And that'll simplify a lot of your circuitry. All right, any issues we're running into with MP-Lab X that we haven't talked about yet? I'll be in there during lab time every time we have lab time, so If anything does come up, just go ahead and talk to me about it. All right, let's talk about programming on the PIC processor. So here's a basic model for a computer. CPU is a central processing unit. It's the brains of the computer that does all the work. And we attach to that some sort of memory, and usually some sort of I/O subsystem. And the memory stores the stuff that you're operating on, the numbers and characters and pictures and so on that your CPU is chewing on. The CPU actually does the calculations, and the I/O is the thing that connects to, I don't know, a keyboard or a mouse or a network interface, or for us, a switch or an LED. And on many modern systems, the memory is actually broken up into data memory and program memory. These aren't always distinct. On these boxes, they're not. On the PIC processor, they are. Program memory is where we store the instructions that tell the computer what we want it to do. Data memory is where we store the numbers that we want it to operate on, the data. And they're separate on a PIC processor. In particular, our program memory stores 4,096 bytes worth of instructions. Our data memory can store 256 bytes of data. So it's a lot smaller than the program memory. And it's a whole lot smaller than a laptop, right? You buy a laptop and it's only got 256 bytes of memory, don't buy it. On the PIC so the I/O subsystem comes in lots of different versions, but on the PIC processor, the I/O subsystem looks kind of like data memory. There's certain pieces of data that instead of actually being a register that we can store numbers into or read numbers from, it's a location that actually interfaces with something in the outside world, like a pin. So there's certain locations that if I write the number into some location in the data memory, it's just a number. It gets stored in that location. And if I ask what's in that location in data memory, it's whatever number I just stored. But there's other locations that I can write to that are actually part of the I/O subsystem. There's one location in particular that if I write this number into that location, it drives 5 volts on one of the pins of the PIC chip. And if I read from some location in here, I'm actually reading the voltage level that's being applied to pins on the PIC chip. And there's another location that if I write into, it starts to set up this timing subsystem. So we can generate events every 3 seconds if we want. And there's another section that if I read from, it's actually reading an analog voltage coming in and telling it how to convert that into a digital number. So there's this whole subsystem for doing input-output, but it acts like a data memory. It's just particular locations in our data memory don't actually correspond to general data. They're I/O functions. And so these are called special function registers, or SFRs. And we'll be doing a lot with SFRs in this course. It's how you get out of the box, basically. All right, well, let's look at our data memory. So 256 bytes. Our basic unit of data is a byte. How many bits in a byte? 8, right? So 8-bit number, small integer, 0 to 255. That's the type of variable we're working with. And yeah, in terms of a PC, that's minuscule. But we're not trying to do things on a PIC that we do with a PC. We're trying to do things like read this sensor, convert it into temperature. If the temperature goes above a certain amount, turn on this alarm. That would be a typical application for a PIC chip. Why? Because it costs $1. And it's a small chip, and you can put it on a circuit board and build it into your lab, right? And have it monitor temperature for you and sound an alarm if the temperature gets too high. So we don't need a whole lot of memory for these kinds of things that we're going to be doing. So 256 variables, if you will, where your variables are just small integers. And our data memory looks something like this. 8 bits wide, 256 locations. And so we can just think of this as a big bin of 256 bytes. And in order to identify which piece of data we want to work with, there's an address associated with each of these. The address goes from 0 to 255. All right, we're rarely going to work in decimal in here. We're almost always going to work in hex. So, what is 255 in hex?
It's like 4 F's, isn't it?
It's actually only 2 F's. So F is 15. 1 hex digit gets you from 0 to 15, 2 gets you from 0 to 255. 4 will get you 16 bits worth. And we tend to put leading zeros in front of hexadecimal numbers if we know we're talking about an 8-bit number, right? And we need 8 bits to specify one of 256 locations. So those are our hex addresses for our data memory. So 8 bits let us specify which piece of data we're interested in. So when we're writing a command for the PIC chip, when we're asking it to do something, there's usually 2 things we need to specify. Basically a verb and a direct object. So an opcode and an operand. This is a verb, this is a direct object. This is what we want the computer to do, this is what we want it to do it to. And that's what most of our instructions look like. So what are some examples? CLRF, which is short for clear a file register. In this data memory, these are called file registers. To me, that's a peculiar notation for PIC processors. Most other systems will just call those memory locations or variables, but they use the word file register. So clear F, CLRF, clear file register. We're asking the CPU to zero out some location in our data memory. Well, we've got to tell it which location to zero out. So if I say clear F, and I'm going to say 0x to tell it that I'm in hexadecimal, so it's just like in C, put 0x in front of something. So I'm saying clear file register 3. If this instruction gets executed, the CPU is going to write 8 zeros into that location in memory. So this is clear file register. Another instruction is increment file register, INCF. This is what we call a read, modify, write. To increment file register 3, it means do 3 things. 1, read what's in this file register right now. Then add 1 to that value, then write that new value back into file register 3. So this will read register 3, and we just cleared it, so it reads a 0. It adds 1 to 0 and gets a 1, and then it writes that back into file register 3. So now this is what register 3 looks like. If I repeat that instruction again, what's it going to do? It's going to add another one. It's going to read what's in register 3, which is currently the number 1. It's going to increment it, add 1, which makes it a 2, and then write that back in. This is going to be decimal number 2, which is binary 1, 0. And these are the size of the chunks we're going to be working with. Right, just these really simple operations, clear, increment, decrement, and so on. So it's going to be these tiny little pieces. All right, so what kinds of instructions can we do? We looked at table 20-1 briefly on Tuesday. Clear, increment, decrement, complement. If I were to say complement file register 3, that means read the current value of this register, which is all zeros except for 1 here. Complement means change your 1s to 0s, change your 0s to 1s, and then write it back. So instead of being all zeros with a 1 in that second position, this becomes this. Well, this is great, but it's pretty limited, because the way we've set this up, our verb is always acting on exactly one thing. Increment this register, decrement this register. How are we going to do something like add 2 file registers together? So suppose I want to read the contents of file registers 3 and 4 and add them together and store the result in file register 1. So let's write a comment. I want to read 2 file registers, add their values together, and store the sum in 0, 1. And I'm not trying to add 3 and 4, okay? I'm trying to add what's stored in file register 3 and file register 4. Add those values and store in file register 1. And the short answer is we can't do it. At least not with one instruction. There's no instruction to do this. Why? Because this chip costs $1. All right? This chip is what's called a reduced instruction set. This, with a 64-bit Intel processor, is what's called a complex instruction set processor. It has thousands of instructions that it can perform, some of them very sophisticated. This PIC chip is a reduced instruction set computer, a RISC machine, RISC. It has a few dozen things it can do, and most of them are pretty rudimentary, increment, decrement. And in particular, we can't ask it to add the contents of two file registers together. That's a problem. So there's got to be a workaround for it, and there is. There's a special file register. It's called the working register. And some of these instructions that take two operands can be told to automatically assume the working register is one of its operands. So we don't actually specify add this location to that location, but we can say add the contents of this location to the contents of the working register. So if we want to add the contents of registers 3 and 4, we need to do something like this. Copy file register 3 to the working register, and then add file register 4 to the working register. And we can save that in one of two places. We can either save it back in file register 4, or we can save it in the working register. If you don't want to destroy the contents of register 4, let's save this in the working register. So now this is the sum of file registers 3 and 4, and we wanted to store that in file register 1, so now we can say copy contents of the working register into file register 1. So it takes 3 steps. Now, when people first started talking about this, people poo-pooed this idea because you got to do 3 instructions just to add 2 numbers together. How efficient is that going to be? But the reality has been, because you only have a small set of instructions on this machine, it's very easy to design. A Pentium processor, to get to the next generation of it, is a huge effort. It takes thousands of engineers, hundreds of millions of dollars probably in research and development costs, because it's such a complex architecture. But a PIC processor or some other RISC processor is a much simpler design, and to re-implement it when we have smaller transistors, when we have faster switching technology, is a relatively inexpensive process. And so even though these chips are very simple, and it might take 3 instructions to do something seemingly simple, as the technology has improved, as transistors have gotten smaller and faster and lower power, people have been able to come up with new versions of these chips. And RISC processors have dominated the market. The most popular one being what's called the ARM processor, or the ARM architecture. And you see lots of computers around, right? Lots of laptops and desktops. That's less than 1% of the CPUs out there in the world. Over 99% of the CPUs on this planet are ARM-based. It's in your cell phone, it's in your smart devices, it's everywhere, and it's starting to be in laptops. Right? And even though you have to do more than 1 instruction, you can run these things really fast. Right? Partly because the instructions are so simple. We'll talk about that in detail in a few chapters when we talk about performance and pipelining. And we'll see why having a simpler instruction set lets you crank the clock speed up. So for what we're doing in here, we don't really care about speed. We're running with a clock of around 31 kilohertz, which is pretty slow anyway. But if it takes 10 microseconds for your LED to turn on, it's not going to bother us. So this will work perfectly fine for us. All right, so the working register, WREG, is going to be a big part of how we program this chip. we're always gonna have to use this. It's gonna be a great place for very, very short temporary storage. But it's the only location that we can automatically work with by saying, hey, I wanna take this result and store it in the W reg. So we can't use it for like long-term storage. But as a little scratch pad area, it's gonna be great. All right, so we wanna add two numbers together, copy one of them to the working reg, add your second number to the working reg, and then copy the working reg to your destination. But that's how we can add two things together. So let's take a look at this table 20-1 again. So here's our add WREG and the file register, add WF. Here's an add WF with a carry. We won't need to worry about that for a little while. But when you do addition in 250 and you made that full adder and half adder, the full adder took an incoming carry bit and added that to 2 bits. And that was so we could take one adder and put them together side by side. Well, this thing only works with 8-bit numbers. What if you want to add 2 16-bit numbers? Can you do it? Well, you can't do it directly, but it's not too hard to do indirectly. Here's a 16-bit number. Here's a 16-bit number. I'll break them into 2 8-bit pieces. We know we can add these 8 bits and these 8 bits and get an 8-bit sum. And we know we can add these 8 bits and these 8 bits and get an 8-bit sum. But that may not be the correct answer if adding these two generated a carry coming out of that 8-bit. We need to add an extra 1 to this and this. So this instruction will let us do that pretty painlessly. And we'll play around with that in another week or 2. So AND WF does a logical AND instead of doing addition. So suppose file register five contains this number. And suppose my working register contains this number. So if I say AND WF 0x05, this says I want to do a logical AND of the contents of the working register and the contents of file register 5. When you AND 2 bits, right, the result's 1 if both bits are 1, 0 otherwise. When you AND 2 8-bit numbers, you just do it bit by bit. 1 and 1 is 1, 0 and 1 is 0, 1 and 0 is 0, 0 and 0 is 0, 1 and 1 is 1, 0 and 1 is 0, that would be the result. We're going to do that a lot. We'll see why in a little bit. But we're always going to be ANDing and ORing things. Alright, clears the contents of a file register, complement, toggles 0s to 1s and 1s to 0s. We're still not going to talk about these compares. Decrement, we won't worry about that. Increment, inclusive OR, that's just a plain old OR as opposed to an XOR. And then we get to move. So move the contents of a file register somewhere. Well, like all these other instructions, move can be told to assume that one of the registers you're working with is the working register. So if you have a number in a file register and you want to copy it to the working register, this is what you use. You say move file register whatever into the W register. All right, that's enough of those. So this is the point where we want to look at how these instructions are actually stored in program memory. And that's going to help us understand how we actually write things in this language. So let me start talking about that. And then we'll take a short break. So first of all, these instructions are broken into different categories. These ones we've been talking about, these are called byte-oriented file register operations. There's 5 groups of instructions. This is the first group we're looking at. And these are stored as 16-bit numbers in program memory. And this is a template for how we write one of these instructions in binary. So suppose I want to take an instruction like add working register to file register 5. So and let's say I want to store the result back in file register 5. All right, to represent that in binary, I need to do the following. I need to store 6 bits that specify the opcode. Okay, that's going to be the thing that says I want to do an add WF. And then I have 8 bits down here to specify the actual file register. Remember, we have 256 file registers. That's 8 bits worth of address, 00 to FF. So since I'm trying to add file register 5, I would put the binary value for 5 in here. Which is just that bit pattern, 0101. All right, this destination bit is the one I want to get to. Because if I say add the contents of file register 5 in the W register, it's clear what you're adding together, it's not clear what you're doing with the result. And you always have a choice. You can either store it back in the file register that you read from, or you can store it in the working register. And this bit here tells you which of those you're going to do. So if you set this bit to a 0, then it stores the sum back in the working register. If you set this bit to a 1, it stores the result in the file register. So when I specify add WF 0x05, I need to specify one more number after here, which is the destination. In this case, I want to store the result back in location 05, the file register, so I need my destination bit to be a 1. So my full instruction would be add WF 0x05, comma 1. If I had said comma 0, it would still add those things together, but the sum would get written to WReg. Is that clear? So the opcode says what you want to do. The file register tells you one of your operands. If you need a second operand, it's always the WReg. And then the destination bit says where do you write the result? Back to the file register or into the W register. We're going to ignore the A bit for a moment. So don't worry about that one. All right, so ponder that while you stretch your legs for 5 minutes, and then we'll start coding some instructions.